In March 2026, Google Research published a new method for compressing artificial intelligence models. This mathematical framework sent immediate ripples through the global semiconductor markets. Within hours, shares in major hardware suppliers like Micron and Western Digital fell between 4 and 6%. Investors reacted to data suggesting that the physical demand for high-bandwidth memory chips could be significantly lower than previous forecasts. The central constraint for any AI user is VRAM, or Video Random Access Memory. This is the high-speed physical memory built into a graphics card. If you want to run a large language model or analyze a massive document, you are limited by how many numbers your hardware can store. Because of these physical limits, running the world's most capable AI models has been restricted to those with access to expensive, enterprise-grade hardware clusters. A primary consumer of this memory is the KV cache. The key value cache is a digital storage bank where the AI keeps the context of every word it has already processed, allowing it to generate the next word without repeating trillions of calculations. This cache behaves like a bucket that grows linearly with every word processed. For high-end models, maintaining the context of a long document can require 85 gigabytes of memory, exceeding the graphics card's capacity and causing an out-of-memory crash. Google's Turboquant algorithm reduces the memory required for that cache sixfold. It compresses data to just 3 bits per value while maintaining exact output accuracy. This math reduces the hardware requirements for long-context AI, allowing a machine with limited VRAM to handle workloads that previously required a specialized server. Standard AI compression often works like a low-quality JPEG. It makes the data smaller but introduces noise that causes the AI to hallucinate. To fix this, older methods store extra high-precision numbers called quantization constants, but this metadata can take up nearly as much space as the data itself. Turboquant avoids this using a technique called polar quant. It shifts the AI's data from a standard Cartesian grid, a flat coordinate system using X and Y axes, into a circular polar coordinate system. Polar coordinates map data points based on their distance from the center and their specific angle. In this polar view, the complex numerical weights of the AI align into highly predictable angles and radiuses. This geometric alignment allows the system to compress the data without storing the per-block normalization constants required by older methods. By removing that metadata overhead, the total memory footprint drops without losing information. By changing how the data is viewed geometrically, researchers eliminated the metadata that typically makes high-ratio compression inefficient. Even with this new geometry, aggressive compression leaves behind tiny rounding errors. If these small discrepancies are not corrected, they accumulate over a long conversation, eventually causing the AI to provide incorrect or nonsensical answers. Turboquant uses the QJL transform, quantized Johnson-Lindenstrauss, a 1-bit filter identifying remaining error spikes while preserving data relationships. As the AI calculates, this zero-bias estimator ensures positive and negative rounding errors cancel each other out, making the compressed data statistically neutral. This process is data oblivious, meaning it doesn't need to be calibrated on specific documents. It is also training-free, so it can be applied to an existing AI model as a drop-in optimization without needing to retrain it. Turboquant achieves its accuracy not by avoiding errors, but by using a 2-stage mathematical process to cancel them out during the calculation. Running a 70 billion parameter model typically requires an 85 gigabyte memory cache, demanding an expensive server. But Turboquant reduces that to 14 gigabytes, fitting a high-end consumer GPU. With a 6 times smaller cache, users process 6 times more text on hardware they already own. The effective capacity of the memory already in these systems has increased 6-fold through this algorithmic change, fundamentally rewriting the rules of local AI. Within hours of the paper's release, developers began integrating Turboquant into open-source engines like llama.cpp and MLX. These tools allow individuals to run AI locally on their own machines without relying on cloud servers. The community has already produced derivatives like RotorQuant. This variation uses Clifford algebra, a type of geometry involving rotations and reflections, to make the compression even more efficient on the latest generation of AI hardware. These developments suggest that AI progress is no longer defined solely by the physical count of memory chips inside a data center. The primary driver of efficiency is shifting toward the mathematical optimization of the data, using software to extend the capabilities of the hardware already sitting on our desks.